Welcome back to Plain Explain, the channel where we take the complicated things hiding underneath our everyday lives and break them down into simple human explanations. Today, we're exploring a topic that quietly protects almost everything you do online. It's the reason you can send a message without the whole internet reading it, the reason online shopping doesn't expose your credit card, and the reason the modern world doesn't fall apart every 5 minutes. Encryption. What it is, how it works, and why it matters far more than most people realize. So sit back, because by the end of this video, you'll understand encryption in a way most people never will. Most people don't realize this, but every time you send a message, watch a video, or buy something online, your information goes on a journey. And on that journey, it passes through a lot of places you never see: servers, routers, networks, cables under the ocean. At any point, someone could try to peek inside. But what they actually see looks nothing like your original message. Instead, it looks like random noise. And that's because of one of the most important ideas in the modern digital world: encryption. Today, we're going to break down how encryption truly works. Not the mysterious, complicated version people imagine when they hear the word cryptography, but the real simple foundations underneath. We're going to explore plaintext, ciphertext keys, ciphers, symmetric and asymmetric encryption, and finally, the thing people hear about all the time: end-to-end encryption. And we're going to do all of that using explanations that actually make sense without assuming you're a computer scientist. So let's begin with something very simple. Why does encryption matter in the first place? Every day, enormous amounts of data get intercepted. People try to read emails that aren't theirs. Hackers sit between your phone and the Wi-Fi at the cafe, waiting for someone to send something sensitive. Even entire governments watch traffic flowing across the internet. And without encryption, all of it would be right there in plain sight. Your messages, your login details, your personal conversations, your private photos. Everything. Encryption is the invisible protection system that turns your information into something useless to anyone except the person you meant to receive it. It's the difference between shouting your secrets across a crowded room and whispering them in a locked safe that only one other person in the world can open. So, how does that actually work? Let's start with the simplest idea in all of cryptography: the transformation from plaintext to ciphertext. Plaintext is just your normal message. Hey, where are you? Or send me the file. Or I'll meet you at 6. That's plain text. But the moment your device encrypts it, it becomes ciphertext, a scrambled version of your message that looks like total nonsense. Something like G49PK7AA3JB1. If someone intercepts it, that's all they see. To them, it's basically alien language. The magic, though, is that this transformation isn't random. There's a method behind it. And this is where two essential ideas appear: keys and ciphers. Let's talk about keys first. Keys are the heart of encryption. If ciphertext is a locked box, the key is what opens it. Without the key, the locked box might as well be a rock. With it, everything inside makes sense again. You can think of a key as a secret passcode. Imagine you and your friend agree that every letter in your message will be shifted forward 3 positions in the alphabet. A becomes D, B becomes E, C becomes F. That 3-letter shift is essentially your key. If someone else doesn't know the shift, they'll look at your message and have no idea what it says. But today's encryption no longer relies on keys that simple. Modern keys are huge numbers. So huge that even the world's fastest computers would need more time than the age of the universe to guess them. And that's not an exaggeration. Keys aren't guesses. They're mathematically constructed to be impossible to brute force. That's why they're so powerful. But a key by itself doesn't do anything. You also need the cipher. So what is a cipher? A cipher is the algorithm, the rulebook, the recipe for how we turn plaintext into ciphertext and back again. If the key is the specific amount of salt in your soup, the cipher is the entire cooking method. The steps, the heat, the sequence. Change the key, and the final flavor changes. Change the cipher, and the entire dish is different. The simplest cipher ever recorded was the Caesar cipher used by Julius Caesar 2,000 years ago. It shifted letters by a fixed amount in the alphabet. Very basic. Today, ciphers like AES Advanced Encryption Standard use layers of substitution permutation mixing and operations that would take an extraordinary amount of time to describe. They're insanely complex. But the beauty is, you don't have to understand the math for them to protect you. The cipher handles the transformation. The key personalizes it to you. Now that we understand plaintext, ciphertext keys, and ciphers, let's explore how people actually use keys in practice. Because here's the real challenge. How do you share a key with someone securely? If you and your friend both need the same key to encrypt and decrypt messages, you face a problem. How do you give them the key without letting someone else intercept it? If a hacker gets your key, everything falls apart. This brings us to an important division in the world of encryption, symmetric encryption, and asymmetric encryption. Symmetric encryption is the simpler version. It uses one key for both encrypting and decrypting. If you lock a message with key X, you also unlock it with key X. Very fast, very efficient. It's used all over the world for huge amounts of data, but it has one flaw: key exchange. Getting the key to the right person safely is hard. If someone intercepts the key, they intercept everything. So modern cryptography introduced something brilliant: asymmetric encryption, also known as public key cryptography. This system doesn't use one key, it uses two. A public key which anyone can have, and a private key which only you can have. These two keys are mathematically linked, but in a way that makes it practically impossible to calculate the private key, even if you know the public one. Here's how it works in practice. Let's say I want to send you a secret message. You give me your public key. I use it to encrypt my message. Now here's the interesting part. Once the message is encrypted with your public key, even you cannot decrypt it with that same key. Only your private key can unlock it. And since only you have your private key, only you can read the message. This is one of the breakthroughs that made online security possible. Every time you see that little lock icon next to a website in your browser, you're seeing asymmetric encryption at work. Your browser is exchanging keys with the website, making sure no one else can read what's going on between you two. But now we go one step further. One of the most popular ideas in modern digital privacy: end-to-end encryption. You've probably heard apps brag about it. WhatsApp, Signal, iMessage, Telegram. They all tell you they offer end-to-end encryption. But what does that actually mean? End-to-end encryption means that your message is encrypted on your device before it leaves your phone and stays encrypted all the way until it reaches the person you're talking to. Not even the company that owns the messaging app can read your messages. They don't have the key. Only you and the person you're communicating with do. Imagine every message you send is a small metal safe. You lock it using the recipient's public key. It gets sent across the internet. Servers hold it, routers pass it along. But none of them can open the safe. When it reaches the recipient, they use their private key, something only they have to open it. That's end-to-end encryption. The ends are the people involved, the sender, the receiver. Everyone else in the middle is locked out. This is a huge deal because it means that even if someone grabs the encrypted message while it's traveling, they're stuck staring at ciphertext. They see noise, not information. So now we have a question. If encryption is so strong, why can't hackers just break it? Why can't a supercomputer just guess the key? Well, the answer is they can try. But mathematically, breaking modern encryption is so computationally expensive that it may as well be impossible. For example, AES 256, one of the most common encryption standards, has two 256 possible keys. That's a number so large it's almost meaningless to the human brain. It's larger than the number of atoms in the observable universe. You could have trillions of supercomputers guessing trillions of keys every second for billions of years and still be nowhere close. This is why encryption today acts like a digital force field. It's not based on secrecy. It's based on math. Unbreakable math. But the future isn't guaranteed. Quantum computing, still in its early stages, could theoretically break some forms of encryption that we rely on today. Not all of them, but enough to change the landscape. That's why researchers are already building the next generation of cryptography called post-quantum encryption. We might explore that in a future video. For now, though, encryption is one of the strongest tools humans have created to protect themselves in a hyper-connected world. Encryption keeps your banking information safe. It prevents strangers from reading your messages. It secures medical records, financial data, government secrets, and the entire infrastructure of the modern internet. Let's summarize the essentials one more time. Plain text is your original message. Ciphertext is the scrambled version. Keys unlock encrypted messages. Ciphers are the methods that do the scrambling. Symmetric encryption uses one key. Asymmetric encryption uses two. And end-to-end encryption ensures that only the sender and receiver ever have the ability to read a message. Together, these ideas are the foundation of digital privacy. They're the reason the internet can function safely. And they're the reason you can whisper secrets across the world without worrying who might be listening. But here's a final thought. If encryption is so essential to privacy, why do some governments keep trying to weaken it? Why do they push for backdoors into encrypted systems? And what would it mean if they got what they wanted? That's a question for another video. Thanks for watching. Plain Explain. If this breakdown helped you understand encryption the way it truly works beneath the surface, make sure to subscribe for more deep, clear explanations on the everyday technologies shaping our world. And if you're curious about the bigger debate around encryption, why governments keep trying to weaken it, and what might happen if they succeed, that's a video we're working on next. Until then, stay curious, stay safe, and I'll see you in the next one.